Welcome to Lecture 8. We're going to be looking at, for this lecture, is looking at land use and soils and agriculture. And this is going to incorporate chapters 13 of 14 of the 12th edition and 12 and 13 of the 13th and 14th editions. That was confusing. So we're going to look at some of the historical forces that shape land use and go primarily into some of our urban development and how we put some land aside, and the whole idea of sprawl, which our Houston area is an excellent example of when we think about this. Also, the problems associated with unplanned urban growth and some land use principles. From there, we're going to go on to a little about land use plans. We're going to see this more in videos, and then look at soil formation and a little about agriculture, because primarily agriculture is an important aspect of land planning and of when we look at how soils are used. So to begin with, why do we need to plan for land? Because we hear a lot of things about land planning and zoning and this type of stuff and that. And land planning goes on at a local up to a national level, and sometimes even there's international cooperation in how we use land, depending on trade and depending on borders. Okay, so when we look at how we use land, we find out that the way we use land today is based on really traditional models of land use. And you're going to see a couple of videos on that, particularly related to urban land use. So most of our planning goes into the development of cities, and eventually large urban areas. And most land use decisions are still based on economic considerations, we're going to see. And that is going to be the primary factor. And what I mean by economic considerations, that means access to resources, and that includes access to space, access to agricultural land, and how do we balance this? So how do we balance an area, particularly that is mixed use? That means it has forest reserves and maybe oil or mineral reserves, and also might be an adequate area to do farming and to set up cities and even have landscapes. So this is a very complex thing when we look at the need for planning and how we go about planning. In this course, we can't even cover much of it. I mean, you can spend 2 to 3 years looking at the whole idiosyncrasies and uniquenesses of different types of land use. So when we typically look at the historic factors that determine our use of land, most urban areas, most countries started out as, agrarian societies. That means agricultural societies. And a lot of our land use, even today, when we look at the United States, 50%, over 50% is crops and livestock meaning everything from cows, chickens, sheep, whatever. And this is still important to think about because we still have to feed our nation. And this number is going down over time. We do see, and we'll see in the next slide, how we find it very important to put away forest and natural areas. And this was the whole intent of Theodore Roosevelt when he came upon the National Park Service. This wasn't something just to have people do recreation, and this was a way of preserving forests and natural areas a lot of times, not only as a resource in themselves, but also as a continual source of wood, paper, and minerals. So we wanted areas put aside that would be used nothing else except as a conservatory for resources. And then we have, in the United States, about 4% of our land is intensive human use. And this is a little low compared to many other areas, particularly when we look at Europe and parts of Asia. We see that this intensive land use, it means large cities, metropolitan areas, are all pretty small considering. Okay, and in other areas make up a large proportion of the land. When we start looking at countries like Japan, this is becoming such a big factor that it's really greatly impacted this to the point where they don't have enough resources to fuel this intensive human use. And patterns of development we're going to see vary differently depending on immigrant experiences, depending on the philosophy, the environmental ethos of that area. So when we look at our own government and how we perceive land use, we found it very prudent, over 100 years ago, to put aside land that we can consider to be wilderness land. Okay, and this tends to be a very sensitive issue because we argue over who owns this land. We've seen battles over this for years. Is this land for forest? Is it for cattle? Is it for agriculture? Does it belong to the government? Does it belong to the people? But we developed in the 1960s in this country what's called the Multiple Use Sustained Yield Act. And this was in response to various, needs on certain parcels of land and competing needs in particular. So we see what we do, guys, is when we start looking at wilderness, we're going to see that still a large part of wilderness is forest. And this is not forest to preserve. This is forest to conserve. That means this is forest that we collect game out of still today, believe it or not, that we harvest wood out of, particularly and there's different types of forests for different types of wood, hardwood and softwood, wood for construction or wood for making paper. We're going to see that we do have managed hunting and fishing areas, and this is done a lot of times through the states and sometimes through the federal government. And then this is more of the aesthetic, where we look at regional and parks and state parks that are just for basically recreation and camping. And then we look at primitive wilderness areas, and these are more used for their ecosystem services. That means we protect them also for natural resources too, but we tend not to destroy these areas, but somehow get what we can out of them while still maintaining their purity. So we can look at all different reasons for why we develop land in different ways, but particularly in what we kind of erroneously call the wilderness, because it's not really a wilderness. It's most of a modified wilderness that allows us to have resources, not just basically the native wildlife. And most wilderness areas today are not made up of the natural wildlife. Now, the biggest issue we're going to deal with this class is urban land development, because we're going to be seeing a global growth in urban areas. And eventually we're going to see by 2050, a majority of the earth is going to be urban. And we're going to have to find some creative ways, particularly to feed ourselves, since that means there's going to be a decline in agricultural land. And also we're going to have to find creative ways to get resources out of our own urban areas, because a lot of this land that we have right now protected for resources is going to be covered up. So when we look at urban land use models, there's various models that get us to understand how do urban areas develop historically. And typically what we see globally is civilizations go from what we call migratory hunter-gatherers. That means the people move around, we go from place to place, finding food, and sometimes, settling for an area a little period of time. And then we go on to what's called a settlement or agricultural area. And this is where the most important part of the land is for growing food. And then a small part of the land is for commerce and trade. That means like small banks or money lenders, like in the old days, the biblical days or the Roman days, and also for markets and trades, so that the farmers can, sell their crops or trade their crops for items, and also buy farming equipment if they can't make it themselves. So what we see typically is what we're going to call the European model or New World model. And the European model you find in not just Europe, you find it obviously in America, Canada, and also major cities where Spanish, British, Dutch, and Portuguese settled. And this is more of what's called a concentric ring or cyclic model. We're going to see that the city, the large city or the financial area, becomes the major focus, and it's surrounded by zones of differential development, where ultimately on the outside we find our farms. And you'll see here, as these things develop, these areas tend to get bigger. Okay, this ring, I should say, tends to get bigger and pushes these further out, assuming that there's land there. We could also look at what's called the modified area, and this is more typical of developing countries. Okay, and we see that rivers become the primary focus of development, with cities forming in a big area. And you see this sort of like in Cairo, Egypt. You have this major city, and then you have everything, all these businesses and houses developed and commerce developing along the river, And then as you move out, it's not so much concentric rings rather than bands that follow this river sometimes from miles, hundreds of miles. So this is again sometimes called the modified model, but it's not only due to rivers. It can be based on major roads and other things, whereas the concentric model you see in Houston is based on what we sometimes call farm to market roads or spokes. And the spoke model tends to cause this cyclic growth that also builds transportation in rings, again, very much like you see in Houston. And I've seen this also in Beijing, where some of these outer rings get to be a diameter of almost like 100 miles, which is kind of crazy when we look at this and how big these urban areas can grow. So in the videos, you're going to learn about 3 urban use models. We're going to look at what's called the typical concentric ring, and I'd like you to know that usually in the center of this ring, this is a very important European model that, again, we find in major cities across the world as Europeans settled and cities tended to take on this model. You find a central business district, very much like downtown Houston. And then as we get outside, we find wholesale and light manufacturing, sometimes heavy manufacturing, and these tended to be the dirty, nasty areas of a city. Okay, we then find a low-cost housing right next to that because these people needed a close commute to work. And why were these located together? Because these industries needed access to the commerce and the financial areas. We then have here sort of like the burbs, the medium cost housing, and this would be more like, you know, Kingwood area and some of the suburbs you see outside of Highway 610. And then we get into more ritzy, high-cost areas where these are the people that sometimes don't commute, but they benefit from the wealth around here. And they live, and in New York, we had an area called Long Island, New York, which tended to be this. And it was famous for being this big area outside of New York City where the people made their money in the city, but did not live in a city and sometimes preferred not to go into it. So that's that little area 5. And then we can have other rings there too that we see in other models. Okay, but like number 6 and 7 here might be incorporated in number 2. But then we have what's called these commuter zones sometimes too, which could be other outer areas. And again, outside of here can be farms. Okay, now this is called the sector theory. And you actually see some of this in Houston area, where sometimes you get a corridor based on a highway or based on traditional land uses or some type of terrain feature, where you have somewhat of a concentric ring, but also these little interruptions of a ring, where you might have, let's say, wholesale light manufacturing going all the way to the city and expanding out to regions sort of like our petroleum manufacturing areas. So these are sometimes occur when you have an area that has a traditional industry that you have not gotten rid of. And then in certain areas, you also have what's called the multiple nuclei theory. And this means that you have a traditional theory where an urban, a financial district developed here, and then there was really all spots of development randomly about surrounding that urban area and sometimes not even connected to it. And we see, and a good model of this you see in Pittsburgh and also in parts of New York City, which is separated into different boroughs, that each borough has its own little area like this. They have their own downtown, they have their own light manufacturing and heavy manufacturing areas, and spattered little houses and suburbs and upper income areas. So, and there's many, many models of urban land use when we look at this. But don't forget that there's agricultural use too that operates on the outside. And like in Houston, you might even find on the inside spattered about, like when you go to the Tomball area, where you find farms kind of right near the airport and also right near suburban areas. Now, the history of most of the world was based on people finding waterways and traveling around waterways. And this became particularly important when people started settling and doing trade. They discovered that trade was best done by water. And when we look at major cities in the United States and where they developed, the primary cities developed around waterways, particularly waterways that they can get from one part of the country to the other, and also go from some type of oceanic area, um, where trade can come in from literally other countries or other continents even, and fill in this whole area. Now, of course, every now and then you'll see what are called highway cities. And that means when you start going through this area here, you might see little splatters of cities that really correlate more with highways and with things like resources like coal and oil and other things. And you see this a lot in Oklahoma, and even Texas, towns that formed on highways that led to coal. But our primary development was waterways. And this is why in many parts of the world, like around New York with the Erie Canal, we even built artificial waterways and canals, and built even an intercoastal waterway system to protect traffic coming across these waterways. And believe me, every pirate knew these waterways were valuable for trade and commerce. And many pirates even went inland as far up as St. Louis and other areas to take advantage of the boat trade. Because they didn't just pirate on open ocean. They pirated in inland, what we would call inland seas too. So many major cities, again, develop on waterways. And from that, they can develop any of those three urban development models you've seen, depending on the nature of the river and depending on the nature of, basically how that terrain and economy forms. Now, what we also tend to see is as cities grow, there's a necessity for urban areas to take over lightly populated areas. And we see that what's called this urban to rural population shift. So as urban areas become more important and more jobs fill in there, rural people tend to move out. And this is very dramatic in the Midwest states, when particularly we see in Illinois all the way to the Dakotas and then through the Texas Panhandle, where rural areas are drying up. Because as agriculture becomes more efficient and also less needed, because we're doing more importing of our agriculture, more agricultural lands disappearing, people are literally leaving ghost towns behind. And as those areas sit and rot, they possibly become future outburbs or suburbs. I mean, suburbs that are outside the normal suburb, and people commute in for literally miles sometimes. Okay, or it could become a very wealthy area where people don't have to commute at all. So, and we sometimes call these gentrified areas. So this is typical of any country, and we see that this became very particularly active in the 1800s of our country, and throughout Europe, particularly in the 1700s with the Industrial Revolution, which drove the construction of cities and the feasibility of large cities, electrification, all of that, and a density of jobs that drove people away from urban areas. And we're seeing this all over the world. We're seeing it in India, China. China is building cities so quickly that people can't even populate in them, but they're getting ready for that rural to urban shift as their population increases. And we even look at Europe, which is most of Europe is one big mega city now that has very little rural area. And this is a problem because it does affect crops, and they do have to import a lot of crops. And this has even happened in early days in Europe during the 14 to 1600 explorations, when people sent out ships to find these resources to come from areas where they couldn't grow or obtain their own because of the rapid urbanization. So this is probably going to be our downfall. This is going to be what really drives our population to the point of having problems, this rural to urban shift. Another thing we see, as urban areas become bigger, more crowded, and as you develop a middle class, we start to see migration from urban areas then to suburbs. And this is primarily driven by this wonderful thing called cars, transportation. And that can include trains, anything that can be commuted on. So cars and trains permitted people now to travel far to their work and be less convenienced by it. I mean, you're not taking a horse that takes 3 days. So This allows particularly what we call this idea of suburban sprawl. That means we take living areas, move them away from the city, and sometimes move them to the most outer skirt areas outside that whole ring structure, and sometimes buying up farm area and range area. So this is just very typical again of how, we develop land. We go in predictable patterns based on traditional ways that we developed, based on terrain, based on, country of origin, and also based on whether we had an industrial revolution or not. So every area now in the world is starting to see suburbanization, and we sometimes call this urban sprawl. And what sprawl basically is, it's somewhat of an unplanned series of events where populations are growing so fast we just build smatterings of little towns like Kingwood, Woodlands, whatever. We just plop these little areas in. And we sometimes call them planned communities, but they're really put in an unplanned way. And it's not the best land use, because sometimes we dig into agricultural land, a land that could be used for better purpose, and sometimes into floodplains like we have around here. And these areas tend to be somewhat low density, okay, with a lot of commercial development. That means a lot of services that serve these areas directly, so people don't have to commute far to get their basic consumer needs. So a lot of the development there is not going to be large manufacturing, but more service industry type of stuff. Zoning comes about, and guys, Houston does have something related to zoning. We just don't call it zoning, but zoning is an ordinance that does control certain development and who can be built next to who. So yes, we are not zoning free. Believe me, anybody that builds a school, has issues with finding, businesses to go along with them. Because, you can't have a gun store in your school, a liquor bar, an adult entertainment business, whatever. And so, there are things related to zoning, different types of ordinances. But zoning is just a way that we can identify land for a particular purpose to take some of that unplanned growth out. And sometimes we have what's called multi-use zoning. That means we can place a small industry commercial area next to housing, and next to high density housing like apartments, projects, or low density housing like single units. So sprawl does have some planning, but a lot of the lack of planning comes when we see rapid urban development and we're just plopping down areas to find places to put people. And again, this is at the sacrifice of farms and other things. So what are the problems associated with not just unplanned growth? Because this is a misconception of your authors, but we're also looking at planned growth. That means as we grow these urban areas, what are some issues that we identify? And these are all things you are living with now, and things that we probably won't ever be within attainment. That means that we won't ever meet federal standards and sometimes state standards, and will get worse and worse as our population increases. Houston area in particular is going to be the third largest city in the United States, if it isn't already larger than Chicago. And we're going to start seeing us grow more and more. We're showing incredible growth as people move into the area. So it's not just us growing in population, as people moving not just from other countries, but primarily from states in which we see a decay of the urban areas and of the jobs. So we're going to see a heck of an increase in air and water pollution that's going to push back our quality attainments and our ability to maintain clean water, clean air. And most of this is to be due to traffic. And I'm going to say this over and over again. Industry is the least of the polluters, except maybe if you get into the middle of a factory. When we start talking about air and water pollution, the biggest users are going to be households and cars. For air pollution, it's cars. And I mean cars. If we get away from cars and go with public transportation, we're going to see an incredible decrease in air pollution. But for water pollution, we're going to see that households are the major ones. They produce a lot of sewage, a lot of other materials associated, runoff and litter and other things, and dog do, you'd be surprised. And the need for landfills also does this. This is where our households put their trash. One thing we see too, as far as water pollution go, is the increased probability for runoff and dirty water flooding. Okay, like what happened to our college. We were inundated with sewage and filthy litter, contaminated water, and water that was also contaminated with petroleum and other things. So as we get what's called impermeable surfaces or impervious surfaces, impermeable or impervious, we see that the cement of your house, the way you do your yards, the building of roads, all causes rainwater not to soak in. We need trees and exposed land, soil, for us to absorb rainfall and to also absorb pollution. Our own trees and soils break down pollution, particularly water pollution, and trees in some cases air pollution. So as we grow, our soils get turned into things that water cannot absorb into. And this creates incredible runoff. And we learned this very well with Hurricane Harvey and with previous storms like Allison and others. What we also see in our urban areas is low energy efficiency. That means we have these ineffective cars, and Texas, Oklahoma, some of the larger states are notorious for being so reliant on cars, particularly big cars. Okay, and this is a very inefficient source of transportation. You go to cities like New York, San Francisco, Los Angeles, Chicago, you have incredible public transportation that takes you everywhere. Suburbs, separation of homes and businesses requires additional driving. You look at areas like the Rice area, Heights. They try to keep jobs near the people. And this reduces a lot of the driving too, and it reduces a lot of inefficiencies, okay, in transportation and again, how we just plan cities. So you can see traffic is a major factor. And again, single family homes is probably one of the worst things we can do too, because they are less efficient than multi-family dwellings, and they use much more to heat, much more to cool, and also are probably involved in much more water usage also. Other problems with unplanned and planned growth, and we just mentioned this a little in the previous slide, is floodplain problems. That means on top of having excess drainage now due to the land use, we see that we build in floodplains, guys. We're running out of land, so we build it in lowlands. And now we just found out, with the Harvey flooding, is that the Barker Cypress area, a lot of schools and houses were built in a known place that was supposed to collect water, and it was kind of forgotten about. And guys, some of the places that collect water can fill up to 10, 15 feet of water, and that's what happened to them. So sometimes we forget about older land uses or don't pay attention to them, and we get so desperate that we build into these areas. And this is very typical of many areas. Texas and the Houston area are just not the only ones guilty of this. So what we see, though, in spite of this, is we tend to see development in a positive way. But also we can see that some of the consequences of development cause economic losses, which we've learned with Harvey, as well as economic growth. So this is all an economic growth thing, development, but it could also lead to economic losses. But the thing is that, guys, when we start looking at development, we have to weigh the economic growth of development versus the loss. And if development brings in more money than the loss, we go ahead with it, because there's always going to be losses and there's always going to be problems. Now, some other issues, and this goes along with the previous slide too. Wetland misuse, we call this. That means areas that are periodically covered with water, we drain. And this is not new. This goes back to the 1400 Dutch. Every culture does this. New York and Boston were built on this. Texas was a swampy area for most of it along the Gulf Coast, and we drained the swamps all the way back to primitive times. So people were notorious for draining wetlands and for building on beaches and filling in these wetlands, these wet areas with soil. Okay, and we have lost, except in Alaska, because they can't do it in theirs. Theirs are too fragile and also don't allow much development. But we've lost half our wetlands. So guys, think about this. We build cities on areas that notoriously filled with water, that have soils that have what's called clay underneath and accumulate water. And yes, we start seeing things like flooding occur, and we see rainfall having major impacts. Another thing we have to consider when we look at land development is another problem with it is when we're in areas that are prone to natural disasters, like hurricanes, earthquakes, volcanoes. When we don't plan for these things, we end up with cities that have major problems. This is typical of the development of particularly California and the Pacific area, which we build major cities on unstable earth that is subject to volcanoes, earthquakes, and regular tremors and lava flows. Hawaii is another area. In Hawaii, they're a little smarter. Most of the development is on Oahu, which is volcanically stable and probably will never be active again, versus the big island of Hawaii, some of the smaller islands, which still have active lava flows, which I got, the privilege to see a few times in my life. So, growth occurs, and we have reached a state in our society where we're looking at some new principles of understanding urban growth and planning. And we're looking at an area that has various names called smart growth, which some people don't like that term because it makes other growth look dumb. We sometimes call it green growth, sustainable growth. And this just means that we try to build cities that are more livable, and livable according to the public. That means through public surveys means I have green space, I don't have to commute far to work, I have access to transportation, I have access to recreation, and my cities or towns are not cluttered and trafficked and dirty. So this is just a recognition of what the public wants and feels is a smart way to go. And again, this is a very similar term to sustainable. So we can look at models of what's called mixed use, where we can have people that have their jobs not too far from their houses, and that means light manufacturing, commercial, and banks and everything nearby. And this is sometimes what you see start developing in suburban areas, is mixed uses, so people don't have to commute far. And what you work into that is also more accessible transportation too, like you see in Austin with the trams and other major cities. Dallas also has and Houston, we have our own short tram, which doesn't go too far, but is still taking advantage of that mixed land use where people can take a short trip between recreation, between parks and museums, to their houses, and also to many shops. So smart growth or sustainable development is our future. And part of sustainable development too is meaning how do we design cities so that resources can flow in and out of them without too much distance. And that means how do we get to grow crops near our areas? And there's all sorts of wonderful ideas coming about by growing growing crops in buildings, literally even in inner cities, and doing small manufacturing in large cities, what we call sometimes cottage industries, that make sure that resources are easy in, easy out, so that when we have a disaster or a breakdown in transportation, is we're not lacking in these resources. And again, so we're really starting to see some neat things coming out of this. And one time we'll probably see urban areas where we grow crops on the sides of buildings. This is already occurring in many areas. So, what are farms and cities built on? They are built on something called soil. And please don't use the big D word. Soil is not called dirt. Dirt is a useless substance, a waste, that you drag in a house or get on your clothes. Soil is a complex component of non-living and living materials. Soil is considered alive. It's considered of having an existence in itself that requires living processes to keep it useful. Guys, a lot of time when we build houses, we take soil trash it and turn it into dirt to build our house on top of it. But typically a soil, you're going to learn, is a very complex thing. And the study of soils, particularly agricultural soils, is called agronomy. And this is an incredible complex science. I remember taking this when working on my PhD, because I did it in the School of Agriculture, even though I was an environmental, physiology person, environmental tox person. I had to study also farms as environments, because they made up a large part of Illinois where I was doing my graduate work. And so we have to understand what soils are appropriate, what are their properties, both living and dead, that we can do farming, build buildings, or even obtain mineral resources out of. So it's a very exciting science. And literally, I mean, you can take dozens of courses in this and still not look at the full complexity of what agronomy is. So where does soil come from? That was part in your habitable planets. And we do learn that soil, basically comes from what we call geological processes. And it's basically, we're going to learn the breakdown of what we call the crust of the earth. The crust being a very thin, kind of flexible layer, not made of dirt, but made of soil and rock, that could be very hard to very soft. And it floats upon this moving cores. So our crust is in constant motion, and sometimes we call it the mantle that it sits upon. Okay, so we're not going to get too much into the geology of this, but understand we live in a dynamic earth that is very much sort of like your skin sitting over your guts. Your skin is a little flexible, it can stretch, it can bend, it can wrinkle, and if you did not, and as you get older, you're going to see your skin start sagging down, very much like the way continents move about the earth. So, so here's this area called the mantle, this outer covering, and the thin skin called the crust, which is where we find the soil. Deep in the mantle, we see a lot of mineral resources here that make certain areas of the crust very important. Okay, when we look at the rocky area, we tend to call rock the lithosphere. So any rocky area of the earth, we call the lithosphere. And we're going to see there's a thin layer below the lithosphere we're not going to worry too much about in this course, called the asthenosphere. And this tends to be a more plastic flowing area, very much again like a river of rock, okay, that our land sits upon. Now, the term plate tectonics we're not going to focus on too much in this class, but basically what geologists have learned is that the earth is divided into these plates of crust that flow upon this mantle, and these are just like little plates, literally, that have their own directional movement. Okay, and they sit and float and they move based on their proximity to the movement of other continents, and also whether they're sinking into the crust or being spit out. So these things are constantly being formed and cycled around. And this is why I tell you the earth is not a permanent thing. All of the continents you see here are just a point in time. They're constantly moving and running each other over and sinking and absorbing and disappearing. And at one time, our earth, literally was a patch all along the equator. And then we moved, the continents broke up, some reformed, and are still moving around today. And this is, of course, where you get volcanoes and earthquakes forming. So the earth is a temporary place. But luckily, this movement is not fast, or else you'd notice it. It is fast when there's an earthquake, but that's very, that's one small incident. But this is a very slow process that allows animals and plants to travel with these plates and make sure that they can survive following the movement. And sometimes they don't survive. For example, if a tropical plate moves quickly, let's say up to the north, we can lose a lot of creatures during that period. So we live on this beautiful dynamic earth where soil is always forming and soil is always disappearing. So when we look at how soil forms, all soil forms from rock. And if you take geology, you're going to learn all sorts of different types of rocks or minerals that soils can form from. And each type of mineral or rock component can produce a different type of soil. But all rock, when it's exposed to the environment, that means wind and water particularly, and changing temperatures, these are the three biggest factors in what causes rocks to break down, is wind, water, even moisture in the atmosphere, and particularly dramatic changes in temperature, what we call the freeze-thaw cycle, or warming and cooling. This causes a process called weathering. And weathering just means that you're taking rock and somehow reducing it in size. We can cause artificial weathering by breaking apart or putting in sometimes a tumbler, which makes the rock break down into little pieces. This is used a lot in the cement industry and the people that build the foundations of houses. So weathering comes in three types. We have what's called mechanical weathering, which is usually some type of physical force breaks down the rock. And that means basically freezing and thawing, which makes rock expand and contract, the action of animals burrowing through rock. Plant roots can break apart rocks and tear them apart, and also sometimes even wind could etch rock. You see this a lot in the Rocky Mountains and into the Great Basin, like area. You see these carved rocks that are mechanically weathered. Then there's something called chemical weathering, where you actually dissolve the rocks. And this could be done by organisms, particularly organisms called lichens. Okay, and they tend to be a strange little creature we're going to see are very important in soil formation. And that was a nice, horrible spelling. That's actually an H, and that's an I. Okay, water, particularly water of different pHs, can break down and dissolve rock into different components of breaking down to little fractions. And then there's a process of loosening rock and soil called erosion. And sometimes this is caused by wind or water or mechanical activities, like people walking over fresh soil or running machinery over soil. And even slopes can do this. So erosion just means you're taking these weathered materials and moving around and loosening them, or separating or doing whatever with them that causes some type of soil formation. So when we look at the geologic processes, excellent example of mechanical fracturing or damage. You see a crack in a big rock, water gets in, and guys, you don't need freezing and thawing to make water expand and contract, but it does it the best. So water expands and contracts when it changes temperature, and that happens to make the rocks crack more, and they crack further, and so on and so forth. And this might then dissolve due to water, or wind might break it down, or even heating and cooling a rock in general might crack it apart, because you don't need water sometimes. Rocks can expand and contract on their own. So this is typical of what's called fragmentation. And even bricks undergo this. The material you build houses can undergo this. This is more of an eroded landscape. And this is when flowing water comes by, and I'll draw that in blue, and just washes away and carves that rock as a river digs itself down into the ground. And also wind can come through too here and blow this stuff through and carve the rock, particularly when there's sand in the wind. Blowing sand, you get this type of etching. That's called erosion. So soil can be formed from geological processes, weathering, and also a type of weathering called erosion, which tends to be more of a finer tuning of that type of soil. So guys, when we look at how much soil is present in the earth, it's a rare commodity. Look at this. When we start looking, not this diagram, but I want you to think about very little of the earth is land. 70-something% of the earth is water, which means we're living on a small usable component that is very fragile, and you can't make more of it. The Dutch try this when they drain, they literally build dams to hold back ocean and try to scarf more land, or we can build dams to build land south of a river. But all of this is temporary, and all of this is not a good answer. Okay, so land itself is pretty scarce, and a small percentage of even the land we live on is land that is called suitable for living or arable. That means we can't even live there for most of the usable land, or we can't grow crops there, so it's almost useless, except maybe for mineral resources. Now, soil itself is a complex thing, and I'd like you to know this. Soil is about 45% to more mineral. And this is actually looking at the typical soil that is used in agriculture. Other soils vary a lot, from sometimes 20% mineral to almost 100% mineral. But soil is mostly mineral. That's what we call the inanimate component, or inert. There's air. That means pockets of air. There's also pockets of water. And some of this water is actually in liquid form. Some of it is water that's actually chemically stuck to the rock and it can't come out. So we see here's this mineral, air or atmosphere, water, and then this green here is called organic matter or humus, not humus. That's a type of food. And then humus is basically humus is basically dead material, plant roots, animal casts, earthworm, dung, you name it. Poo. This is living stuff. That means earthworms, many types of creatures, protists, fungi in particular, they're the most populated thing in there. Plant roots and underground stems, they make up what's called the living component, which is a very small component, but without it, a soil dies. And guys, this is why you have to take care of soil. Soil can die. If there's no air in the soil, plants and animals can't live in it. And it becomes a very toxic chemical environment that can change the chemistry of the soil. You don't want too much air either. You don't want too much water, too little water. And sometimes you don't want too much mineral or too little mineral, and the same is true for humus. So when we look at soil formation, how do we get all these components? Okay, so we have what's called the parent material, and this is generally pure mineral. Climate works on that pure mineral and breaks it down over time. Landscape, topography, that means is that soil on a slope, is it flat, is it near water? All of this affects with the time how the parent material is converted to soil. And then, of course, there's the biological factors. That means living creatures that help to break down the soil. And it's particularly true of plants and fungi and bacteria, which are very good at, in an established area, maintaining and making soil. And guys, once soil formation occurs, you have to have soil maintenance. And many farmers have learned, particularly those farmers in the Northeast United States, which have been farming, since the 1400s, that you could wear out a soil. And if you're not careful with pesticides and other things that control, creatures in the soil to keep them from eating your crops or infecting your cattle with something, you can kill the good creatures that build that soil. And those soils can disappear and blow away. Or they can lose nutrients or lose their water holding capacity in many cases. So these are the factors that affect soil formation. And don't forget time. Soil can sometimes take years to develop. It can take thousands of years, tens of thousands. And this is the problem, like in some areas, like in the tropics, there is so little temperature change that soil formation is very slow. And then in parts of Alaska, where it's always cold, there's little formation of soil. Houston area is so-so. We get about Dallas, where there is a freeze thaw, not much of one, soil formation is very quicker. When you get more to the Midwest, which has 4 seasons, soil formation is very quick. So this is what makes certain areas, like when you deforest them and remove the soil producing factors, that means the proper mineral component, the biological factors, you could cause severe damage that might take hundreds of years to come back. So when we look at what's called the soil cycle or soil formation, okay, this is a series of steps that starts out with basic rock or flat ground that is fragmented by changing temperature, particularly freeze and thaw by water. And what happens is the rock breaks into small particles. The first organisms come in to take advantage of that. And this is still not soil. It's just a bunch of broken down rock. And little creatures called lichens come in. And they help to take the rock and break it down further by dissolving it. And they're kind of like an algae that lives together with a fungus. And they help each other using photosynthesis. And you can see these all over rocks anywhere, and even sometimes on stepping stones on your house and on trees and bricks. They can live just about anywhere where there's an atmosphere that's conducive for growth. And a lot of them don't even need moisture. They can sometimes suck it in through the air, or the fungus can get it from somewhere else. So these are called pioneer creatures or pioneer communities. Usually what happens when the lichens take over, they eventually run out of space and die, and sometimes they're overgrown by other creatures. And as the rock decays, they lose their solid substrate. So, as rock is broken down into tiny little particles of soil, things like simple grasses and what we call annual plants, plants that live only a year, come in and take over this area. And they now, undergo succession where they're replaced by other creatures and other creatures that eventually help with soil formation. So, and they also contribute to the humus component. So a soil is really not a soil. So the mineral part is broken down to particular size particles, varying size particles. Organisms have done their thing in there, including deposited something called humus. And soil is usually maintained by burrowing in animals, particularly earthworms. People knew this for a long time, and Darwin actually, this is one of the early things he discovered, is how earthworms are beneficial to soil. And I think Ben Franklin did a little study on this too. So once a soil forms, we discovered that soil particles come in three forms, from large to small. And these forms are usually age-related as far as their development. That means we can look at large particles, which are called sand. A sand is something you can roll in your fingers and feel it and see it, but it's not more than a millimeter large. I mean, you can literally, it's rough or round, you can roll it in your hand. Gravel is a little bigger. That's not actually a soil particle. It's actually a larger chunk of sand. But when we look at this thing called soil texture, it means what's the size of the soil particle. And we can classify soil texture into what is called sand, and this one unfortunately is left out, something called silt, and clay. Clay is the tiniest and the smallest. And we can look at what's called this soil chart here. We can name soil based on its chemical composition, its chemical composition too, but also based on its soil texture. That means what size rocks is it predominantly made of. And I know this chart looks a little weird, but this is basically saying that for clay, anything here is 100% clay. That means it goes down this way. Anything here is like 10% clay, right here. This means sand. So this means anything up here is 90% sand, 10% sand. Silt, again, 100, 90, 0. So what we can do is name soils based on what they're made of. And clay tends to be obviously soil that's very high in clay and very low in silt and somewhat moderate to low in sand. Then there's a sandy clay, which is high in sand but also silty. And then there's a silty clay, which is high in silt but also sand. And you can figure this out after a while. Loam is considered the perfect agricultural soil because this has a combination of clay, silt, and sand in a ratio of about 40 to 20 to 40 that makes this ideal for crops. And many agricultural universities develop their own type of what's called loam. And some plants require silt loam, which tends to be a little wetter than something called sandy loam. and clay loam, which tends to be very wet, but also can be a problem for many plants. These are almost saturated with water. So farming can take place in a variety of these, but tend to prefer this lump right here. And this is where agronomists spend a lot of time. Now, certain other soils are perfect for building. We tend to like silt, loam, right around here, better for building because it can support a house. It floats it a little, it's not too heavy, and it won't crack. And it doesn't move with water. Sand tends to wash away with water. Clay tends to swell and shrink when there's water or not, and that can tear apart a house and even elevate land. So let's look at soil texture under the microscope. Here is sand. I'm not going to make you memorize particle size, but sand is usually very angular, very small. This is silt, and guys, this is making silt too big compared to the sand. The silt should probably be about that big, you know, and then the clay is going to be a little smaller. It's probably a little chunk of that, but notice that's in plates. So there's your sand, there's your silt, there's your clay. What makes sand neat, it has very large openings in it, which can store large amounts of water or air. But the problem is that water, when it does get in here, will flow right out. So we call these pores, these holes, pores, and it has a lot of macropores and very little micropores. And the whole idea is that water could wash through this very easily, which we call percolation. And that's why if you want to add drainage to an area, you put soil. Soil does not hold on to water, it lets it pass through. And also when you add too much water, it tends to shift around and float around, and that's where you get into quicksand. Silt is what you see along Galveston Beach, San Jacinto River. It's a roundish. It's actually a little more round than this. They just took the same picture and shrunk it. Okay, so it tends to be a little more rounder particle. It's kind of granular, and also it holds a fair amount of water and can stay wet for a long period of time. And then there's clay. Clay is usually a tight, sheet-like particle, and these sheets overlap with each other, and they sort of form platy to tubicular types of surfaces, and even sometimes lentiform, shaped like a lens. Clay particles have electrical charges on them, negative charges, that tend to repel each other so that there's always a space that some water can get into. And the thing about water, guys, is water, H2O, has an electrical charge that sticks themselves to the clay. And that's what makes clay very gummy, is that H2O gets in here, it sticks to the electric charge and makes the clay swell and feel very sticky. And in some cases, if you walk on it, these sheets tend to slip back and forth and can slip and fall on your butt. Unlike sand, you can't sink in it as much. It's very difficult to pull things in and out. It's very sticky and it tends to stay wet. It also has very little oxygen in it, which is not good for plants or animals. Each has its purpose in nature. And this is very important to keep in mind. There's no one good one, one bad one. And generally we mix all these together to form what's called a agricultural grade soil. Now, last but not least, at the large level, we're going to start looking at what does the soil look like from the level of the crust. And we see that soil forms something called a soil profile. Guys, and a way to look at this is look at this down here as ancient earth, and this is new land. So this is sometimes called the bedrock or the parent material. That means this area right now started out as bare land that, believe it or not, was about this high. Yes, it was about that high, but it was bare rock. What you're seeing here is stuff that's protected from nature and weathering and eroding. So it, excuse me, it more or less resembles the bare rock. So you have your old, what we call released formed soil here, which is still rock. And over the years, it rained and this rock disintegrated, it underwent weathering, erosion, whatever, and those rocks broke down into smaller rocks. And of course, this layer did so, did so, did so, did so. So at one time, this land was this high, but it was that high of rock. And as this gets more exposed to nature, this breaks down a lot. And eventually, this reaches what we call a steady state, where the soil reaches a certain depth and no more weathering is occurring. Now, if I scrape this off and throw it away, this will then take on the properties of that, but be a little lower. This occurs in many mining operations and sometimes during urban development. When we scrape soils off the land gets a little lower. So, a soil profile, we usually label it sometimes O to R, and notice that the alphabet is not exactly correct because we discovered the E horizon in certain soils later. So it goes from A to B to C, and then R, which basically means bedrock. And sometimes we have what's called a BC or a BE, E not found in all soils, but it's intermediate. And again, all of these horizons are determined by particle size, by the amount of organic material in there, and also by the parent material and climate that form that soil. So we can see different areas, depending on climate, depending on rock type, have different soils. And just look at this. Particularly the O horizon, which is where we find leaf litter and most of the nutrients of the soil. Look at this. This is what we call topsoil. This means it's O and A horizon, which is very rich in very fine particles, very much like the stuff that we call loam, this perfect agricultural soil. Here it is. And look at this in a prairie area. This is from a prairie. And this is why prairies were the basis of agriculture. Illinois, Missouri, most of the Midwest, all the way up to central Canada. They love this land because crops can grow in it, plants can grow for forage for your animals, and whatever. All of this soil here allows roots and soil formation that can go down, further down sometimes. And some of these soils get very deep. Now look at the A horizon here in tropical rainforest. That means this is where all the nutrients and soil organisms exist. Below that is the E, which means not much is going on there. It's more rock-like. Very little nutrients. All that happens there is basically water washes through that. And you do find tree roots, but they don't get much out of that area. And then look at a desert area. Very similar to tropical rainforest. And this is why, guys, when I look at deserts that are being exploited for mineral use and for mining and also for agriculture and tropical rainforest, when you remove their topsoil to do whatever you're doing, that topsoil can take thousands of years to tens of thousands of years to develop. And it's gone. It's a thin skin. It does not grow back. This area here undergoes what's called cementification sometimes. That means this rock can harden instead of erode, and sometimes it becomes impermeable, and you have to break it apart with dynamite to get rock formation started. And particularly soils that are high in iron, you get this iron-like, the steel-like coating. So, so again, each area has its own formation of soils and its own horizons, and we can test this using what's called a horizon borer. That means a long metal tube we can dig into the ground, and literally if you have the right truck or right equipment, you can dig all the way down a couple of 100 feet and sample the sea horizon almost to bedrock. Now we can't leave out the soil organisms. They are what makes soil live, particularly in two particular areas, what's called the leaf litter. This is an abundance of life that lives on the surface of the soil, and their main job is to basically break down leaves and provide nutrients from the dead leaves. They also break down dead animals too, and some of them prey on each other, predator-prey relationships, but this is an incredible wealthy area right here that is responsible for most of the O horizon. So if you keep scraping off this area like it's sometimes done in farming, you have no O horizons, which is what contributes to soil maintenance, and also nutrient maintenance, because this is where plants get their nutrients. And guys, plants, their roots even need microorganisms and other creatures to keep them alive. Fungi particularly, yeast. Okay. Then there's the burrowing creatures, which live within the pores of the rocks and sometimes within cavities they make. They help to deposit nutrients in the soil. That means they're pee and poo. There he goes. Look, I pooed. Okay, and he's leaving a little behind. And they leave holes that provide aeration and drainage. And these creatures are microscopic creatures called protistans, which live in microscopic films of water on the soil. And again, they can provide nutrients. They provide a lot of things, including even damage by eating plants and doing whatever. And here's a nice earthworm eating some plants and chewing on roots, but it's beneficial. Here's another guy that we find in soil called mycorrhizae. Woo, that's a weird name, mycorrhizae. And don't worry about the two types. This I'm going to call a megaorganism. Mycorrhizae live within the roots of plants, but they can travel for thousands of miles as a clone, growing into the roots of other plants, growing into the soil, and connecting to everything. And we even believe certain microorganisms can live within these things called the mycelium. It means these hollow chambers. So these are cells, fungal cells, that carry nutrients and water for miles. And we learned that they can keep whole forests alive by moving water from one area to another throughout a forest. So if this part of forest right here is having a drought, whoops, I want that in green, is having a drought, the mycorrhizae can take the water from other areas and pull it in there, including nutrients. This is incredible. This organism does it in a way to keep itself alive, but it can help plants communicate and do other things and even break down materials that a plant normally can. This can take raw materials and turn it to fertilizer for the plant. So organisms play a critical role. Please understand that. Now, what is the biggest issue in soils and land use? Most of it is disappearance due to use. The other factor is erosion. That means wearing away of usable soil and transportation of the soil by wind, water, ice into areas where the soil starts lowering and disappearing. And guys, once we lose that upper body of soil, that A horizon, you end up with bare rock. That's going to take years to come back, and you might even lose some of the uniqueness of the minerals above there. And again, this is very prevalent in tropical forests and deserts, which is just a skin of soil, a thin skin. So we see that guys running off of farmland, cities, houses, suburbs, you name it, even parkland, 25 billion metric tons of soil a year. And it gets worse as farms, ruin the soil and undergo what's called desertification. And we start deforesting areas for use of resources and also for agricultural land. We also see that poor agricultural practices causes accumulation of fertilizers and pesticides, which actually harm the organisms that live in the soil themselves. Okay, and also, guys, as we remove forests and we clear areas for cities, wind erosion becomes amazing. Guys, it's really funny to be in New York City or Chicago or a large area that has incredible winds, is at one time those areas were trees and you barely felt the wind. Today, with just the buildings and these big corridors and streets, is that we've enhanced the wind, which has also enhanced wind damage. So as wind passes through buildings and it gets an incredible speed, and it could pass along to farmlands and suburban areas, that literally blows the soil away. And we see this all the time in California, Arizona, and Utah with these huge sandstorms and silt storms that can ride for miles. So when we look at soil erosion worldwide, we can see that, man, the earth sucks right now, to be honest with you. We are seeing incredible amounts of erosion throughout Asia, throughout northern parts of South America, due to extreme intensive agricultural activities and development, and also due to industrial manufacturing. And we're starting to see the Chinese and the South Americans plop huge cities and other areas here. So these soils are rapidly disappearing. Look at us here, agricultural use, this is a moderate rate. And then we get into the peak, and this is where very little is going on because there's very little usable land, to be honest with you. And erosion doesn't occur because there's not much we can do to make the land erode. So if anything, the biggest issue besides loss of land is land that is usable slowly disappearing and losing it to basically nothingness. Okay, what we are learning, and this we're learning from Harvey too and other previous storms, is that if we can protect our waterways from development, we can protect soil erosion. Because most of the soil erosion around here is from flooding that comes in and strips soils and banks away. And we're also going to learn that by protecting erosion, we're also protecting the Gulf and oceans by preventing that soil from eventually getting into the water. And guys, we lose tons and tons of soil a year into the Gulf of Mexico. Okay, and every area that has a river that leads into an ocean deals with this. And that silt, that clay, that sand can be toxic to a waterway. It can cover up shellfish, it can choke up fish, it's sometimes like broken glass when that stuff spreads through the water, its effect on wildlife, and it can literally just cover up things. It could also block sunlight, which kills off a lot of algae and corals in the ocean that our Earth relies on for 80% of its atmosphere. The oxygen in the atmosphere comes from the oceans. And soil erosion is one of the biggest issues for it. When you look at construction around here, you see things called silt screens. And these are special areas that try to catch erosion. And we also tend to build greenways around where water runs off to try to catch that sand and silt and whatever and embed it into the plant roots and make a new soil out of it. So last but not least, read your chapter about soil conservation and practices. And eventually we're going to do a little case study for fun, kind of, over the holidays, in which you're going to apply practices of survival and agriculture and everything that we learned in this class to look at how can we survive in an environment that can't provide us with the resources we need. How do we modify it? Okay, and how in some cases do we create our own grown environments that we're not used to. So we're going to see that when we look at soil conservation and protection, most of that comes from the agricultural world, because they're the ones that can't affect the land loss. They're the ones that can't deal with the flooding. And we're going to see that they're the major driver in soil conservation. And worldwide, we're starting to see a growth in this, not only the United States, but also developing countries, because this is where they have to put their money. So guys, in this chapter, as part of a summary, please understand, mostly, how do we develop urban areas? How do we make use of land? What are the major principles of using land? And know that it's economics developed, that we look at the benefits of it versus some of the risks. And if the economics of developing land is more than the losses we get from losing that land to, other things, we run with it. And that soil is a growing living entity. I mean, this is how we look at it. I'm not trying to be, funny about this. We treat it like a living entity that can die and erode away. And guys, and land takes a long time to form. We learned about this when we covered succession. Soil formation is part of succession. And if an area gets damaged and the soil cannot come back, nothing could occur. You end up with a wasteland like the Sahara Desert. And again, understand that soil conservation practices, guys, are mostly going to be ways that we reduce erosion. That means loss of soil, not formation of soil, because erosion takes soil from one place and puts it in another. So yes, it can form soil in another area, but for the most part, it's taken away economically important Sahara Desert. And again, understand that soil conservation practices, guys, are mostly going to be ways that we reduce erosion. That means loss of soil, not formation of soil, because erosion takes soil from one place and puts it in another. So yes, it can form soil in another area, but for the most part, it's taking away economically important soil. So on that note, I'm going to leave you. If you have any questions, email me, but please read your book on this and watch the accompanying videos on this. So I will say goodbye for tonight, and we're going to draw glasses on Mr. Bean and whatever. Good night, and